Alright, next topic for us is what are called conjugate addition reactions. These are more properly what we saw back in the dying chapter, a 1,4 addition. Whereas things like a Grignard reagent would be more of a 1,2 type addition, where we're adding, temporarily at least, something to this oxygen, which is atom 1 of the 4-atom functional group. If I could count to 4 would be good. And something else will be adding here. So that is where the terminology comes from. We're using this as a complete conjugate system, so we're using the four atoms, 2 pi bonds, as a single system. So we use the term conjugate addition, but technically it's a 1,4 addition, much like we saw in the past, but it has resonance at the end. So basically, if we drew resonance structures, the only places we're going to get cations that are realistic are atom 2, the carbonyl carbon, and atom 4, the so-called beta carbon, if we're doing the alpha-beta labeling. So depending on what we're using, we're going to go to different spots. If we're getting with something that's really strong, we're going to be preferring direct addition to the carbonyl. If we're getting something that's a little bit less nasty, a little bit more tame, we're going to prefer addition to the carbon instead of the carbon-carbon double bond instead of the carbon-oxygen one. Now, there's a much more in-depth discussion to be had about that. Your book covers it in about 1 page, so you could probably write an entire textbook on it. It goes under the names hard and soft acids and bases, and it's a good bit more complicated than they're giving it credit for. But again, you're not in the graduate program yet, so you don't need that right this moment. But it is not nearly as simple as they're making it out to be. Okay, so here's what I was getting at. If I have a really strong nucleophile, like a Grignard, where I have very much negative charge localized on the carbon of the Grignard reagent, it's going to go straight for that. It's not going to have any interest in that carbon-to-carbon double bond. Basically, it might as well not even be there. We're not going to touch it. The other type of problem is when we have a copper. Now, it's worth pointing out right here is that I could also have used an alkyl lithium here. So an alkyl lithium instead of a Grignard reagent would do exactly the same thing. We're talking about S-block metals. We're talking about relatively small metals. So we're not really doing much to help delocalize that negative charge. When we look at the copper reagent down here, it's a little bit odd. And no surprise, it does something different. We're looking at a transition metal for starters. We have 2 of the alkyl groups. This is going to be a little complicated to look at, so that's where we're going to start, because if you don't look at it, you don't know what it is. It's made like this. If I started with my lithium reagent like this, sometimes you'll see it drawn as covalent like this. It probably is not really good to do it that way, but you'll see it drawn both ways. For our purposes, it's probably a little bit more sensible to draw it as ionic. If I treat that with copper 1 iodide or copper 1 bromide, I'm going to need 2 of these. What I end up with is losing lithium iodide. So one of the lithiums from these 2 are gone. And what I get is a mixed metal complex. So what's called sometimes an organocuprate or dialkyl copper lithium. But basically it looks like this, where those bonds really are much closer to being covalent. And since they are what we would consider in the previous slide to be weaker nucleophiles. So we have something that's a little bit odd here. We're on a much larger metal. It's a transition metal, so its bonding is a little bit different than a main group lithium in a 1s block or an s block metal, an s1 metal. So this is our nucleophile. It's not behaving as if it were an isolated R- anymore. Now, we're going to write it that way. Again, we don't want to overcomplicate our description right now. But essentially, this is what's coming in to here. It's not what we isolate when it's over, but it is our nucleophile, which then the alkyl group shifts afterwards. But the point is, the reason our outcomes here are different is because our nucleophile is drastically different. And it's worth keeping that in mind, because otherwise it looks like, well, why is an anion adding one way in the top and not the same way in the bottom? It's not really the same anion. It's very different. So keep that in mind. It's going to explain why this is a different outcome. So there's a problem with this as well, but just to get past the 1,4 addition thing. Here's my 1,4 addition, there and there. Just if I had added, like, remember when we added HBr to a diene, we ended up with the alkene in the middle, and then our hydrogen off here, and then down here, so that this was 1, 2, 3, and 4. Here's 1, 2, 3, and 4 with the alkene between carbons 2 and 3. Well, if I do that here, 1, 2, 3, 3, and 4. I'm having a real problem counting to 4 on that structure today. Well, then again, here's my 1. My remaining pi bond is between 2 and 3, just like it was down here. So that's the same as it was here in the thermodynamic 1,4 addition. And my new atom, the hydrogen here, is on atom 1, just like it was here. And my nucleophile, in this case, ended up on atom 4, which is where the bromine ended up in that HBr addition. So it's a very similar problem. Now, after we get to that, we're looking at tautomerization back to the carbonyl group. So we get our aldehyde or ketone back. But your book has kind of missed something that I consider to be important here, and that is this is not the end, necessarily. There are some really good stuff we can do here, and some of it very important in historical terms when it comes to organic chemistry. So, here's what that means. If I take a simple example and say, all right, I'm going to hit this with a copper reagent. If I did what that textbook just said, well, it's coming here, and then we're breaking that and ending up here. So this is my nucleophile, and I end up here. So I get an enolate, I have an alkoxide, and I have an R group. In this case, a methyl group. So let's go back and write it properly. There. What they're doing is suggesting that, well, at the end, you just put water and, maybe acid into that, and you get your ketone back, which is fine. But it's definitely not the most useful trick in the world because we can do better. Here's what I mean. This is an enolate, which means I can go from there into an enolate reaction if I want. So let's say I wanted to put something here. I can. All I have to do right now to make that work is put in whatever I want. Let's say I want to just put in an ethyl group. So I'm going to take this and dump it in there, and the enolate is going to react with that, just like it does any other electrophilic carbon. It's an SN2 reaction. We've done this already in previous explanations. Important difference, though. We have some stereochemistry here, depending on what this group actually is. But primarily when we do this, we end up with the product being trans. So I don't have control over which trans. It's only relative stereochemistry. So I would have this and this, the enantiomers of that trans. But the point is, I don't have to just use this as a one-step process. It's most useful when I do it as a two. This is actually a big part of early syntheses of prostaglandins, important signaling molecules, where they have a 5-membered ring with groups that are trans on those 2 carbons and either a ketone or an alcohol here, which I could turn this ketone into an alcohol relatively quickly, sodium borohydride, and I'm there. So the point is, that second reaction coming off this enolate intermediate is a very useful thing that your book doesn't even mention. I think you need to know that because it's a part of making a lot of big molecules, both historically and currently, in organic synthesis. It's the most common, most important usage of this particular reaction is to take it into being able to functionalize 2 different sites with controlled relative stereochemistry. That's relatively important. So back to your originally scheduled program now. So what happens, though, is a little different if our nucleophile is an enolate. Specifically if it's a stabilized enolate. So something like this, where we end up with an enolate between 2 carbonyls, or if I end up with an enolate with something else on one side or the other that is electron withdrawing. So it doesn't really work well with a straight up single carbonyl enolate. What I get is conjugate addition. So I'm adding here, And so this is that carbon, and here's that bond. So I added to the 1,4 addition, so I get a chain extension like this. When we do that, it's called a Michael addition. And the idea is that we have an alpha beta unsaturated acceptor, and we have an enolate as our donor. And we end up with a 1,5 dicarbonyl system. So this is carbon 1, and this is carbon 5. And we'll have something else here, in many cases another carbonyl group, to help stabilize that. So here's an idea. We can get away with something other than an aldehyde on the end of the alpha-beta unsaturated system. We just need something to let us form an enolate after the addition. So we have a lot of possibilities. The aldehyde, the ketone, we've already talked about. The ester we did with the aldol reaction, shouldn't really surprise you. The amide, a little less common, but still viable. Nitriles and nitro groups, again, not as common, but still capable of the same type of resonance problem, so capable of doing the same job here. In terms of stabilized donors, diketones, diesters, ketoesters, and then other stuff. Here's what I meant by other things. If I have a nitrile out there, I can actually stabilize that. If I have a nitro group there, I can stabilize that more aggressively and therefore not even need two different stabilizers or two different electron withdrawing groups to make it work. And of course, this also. We generally don't refer to that as a Michael addition. We just refer to it as a conjugate addition. Michael addition usually means an enolate. So your book is taking a little bit of a strange liberty with the terminology here. But the point is it allows us to add in a conjugate sense.